Rotational kinematics equations. Radians, angular displacement, angular velocity, and angular acceleration are the mathematics tools that are needed to solve rotational kinematics problems. The equations for translational, linear kinematics are presented first. They serve as a base for creating the rotational kinematics equations. These equations are only valid for cases involving a constant acceleration, and we're talking about the linear right here. This allows gravitational problems to be solved, right, where acceleration is g, a constant, and they make it possible to solve kinematics equations without calculus. When acceleration changes, the problems are more complex. The translational kinematics equations, and they are only used with constant acceleration motion. So here's first, v is v0 plus at. Second kinematics, x is x0 plus v0t plus 1/2 at squared. Third kinematics, which combines the first two, v squared is v0 squared plus 2a delta x. And then this one here, average velocity is initial velocity plus final velocity divided by 2. For each of the translational kinematics equations, there is an equivalent rotational equation. Shown is the derivation for angular displacement starting with linear displacement. Angular velocity and angular acceleration use a similar process. Basically, each translational variable is replaced with its rotational analog. So here's our linear equation. I'm going to divide both sides by r. And then, what do we have? Well, x over r is theta, x0 over r is theta 0, v0 over r is omega 0, and so forth. Here are all of them. We've been using delta s for linear displacement because we were talking about a circle, but we can also use delta x. It's just the distance. Similar to the translational equations, these only work for constant angular acceleration this time, for our angular variables. The equations with a star are included on the AP Physics 1 equation sheet. So if you'd like to pause it right now and just do a quick review, and then when you're ready, move on to the next slide. The rotational motion equations also work as part of the equations for rolling motion. Rolling motion is a combination of rotational motion and translational motion. The wheels on a moving car experience rolling motion. The wheels are rotating, which shows the rotational motion, and the wheels move forward as they rotate, showing translational motion. Translational and rotational kinematics equations are used together to solve rolling motion problems. A tricycle wheel of radius 0.55 meters is at rest and is then accelerated at a rate of 1.2 radians per second squared for a period of 10.5 seconds. What is the wheel's final angular velocity? What is the wheel's final linear velocity? This really works just the same as we did when we did linear kinematics. We start with omega is omega 0 plus alpha t. In linear, of course, that would have been v is v0 plus at. Substitute in our givens, and we get 12.6 radians per second. We now want to find the linear velocity. Well, that's just omega r or r omega, same thing. Substitute in our angular velocity there, multiplied by the radius, and we get 6.9 meters per second. A potter's wheel is rotating with an angular velocity of omega 0 equals 2.6 radians per second. The potter applies a constant force, accelerating the wheel at 0.15 radians per second squared. What is the wheel's angular displacement after 12.5 seconds? Now we're going to use the second angular kinematics equation for displacement. Since they didn't give us a starting point, we'll assume that theta 0 is 0. We plug in omega 0. Here's our time, plus 1/2 alpha t squared, and be sure to square that time. That's a fairly common mistake. And we get the displacement is 44.2 radians. A wheel starts from rest and rotates at a constant acceleration of 0.75 radians per second squared. What is the wheel's angular velocity when it describes a total angle of 6.0 radians? And now we have our third kinematics equation, this time for rotational motion. Omega squared is omega 0 squared plus 2 alpha theta. Solve that for omega, and what's our initial angular velocity? Well, that would be 0 because you start from rest, so that disappears. Substitute in our numbers, and we get omega is 3 radians per second.